Okay guys, we're going to cover dividing numbers with exponents today. So to get us started, let's look at an example. So this is what I mean by division. Please remember when you see a fraction bar, that means division. So here's our fraction bar. That means divide. If you didn't know that, good idea to write it down. Let's use the expand and evaluate method to do this. So expand and evaluate. What does that mean we are going to do? That means we are going to do 3 to the fourth over 3 to the second, and we are going to expand the numerator and the denominator. So since we see to the fourth power, now here's what I'm going to do. I'm going to put parentheses around the numerator, around every numerator and every denominator. There's an invisible set of parentheses. Sometimes it makes sense to make them visible. Sometimes we can leave them invisible. For this, I'm going to make them visible. Now we know how to expand bases by now, so we see how there's the exponent is 4, so that means we're going to put 4 blank spots, and we're going to put the base 3 in each of those spots. Down below, for 3 to the power of 2, I'll put 3 times 3. There we go, 3 to the power of 2. All right. I'll take back what I said about the parentheses. You guys can leave the parentheses on your paper. I just believe that it makes it more organized when I take them off. Okay, so I'm going to do something here that might seem unusual, but hopefully we can make it work. I am going to, since we have 4 factors on top, I'm going to split this up into 4 fractions. And then we see we have 3 and 3, 3 and 3. And now the tricky part is that I have 3 over apparently nothing. But remember, we can always put an invisible 1. So I can actually put a 1 there and another invisible 1, because multiplying 3 times 3 is equal to 9. 9 times 1 is still 9. 9 times 1 again is still 9. So we're not changing the value, but these 1s are going to help us. Okay. So I didn't explain this yet, but the reason I'm allowed to split up into 4 little fractions instead of 1 big fraction bar is because the rule, as long as there's just multiplication in the numerator and just multiplication in the denominator, I'm allowed to split them up like that. Because I could go reverse here. I could, if I was to actually try to do 3 over 3 times 3 over 3, I would just do the top times the top and the bottom times the bottom. So we would bring this back to 1 big fraction anyway. But that does not help me with my explanation. Now let's think about this. 3 over 3. That's a fraction, and I actually want to put it in its lowest terms. I know that I can divide both the numerator and denominator by 3. So actually, in lowest terms here, we are going to have 3 divided by 3 is 1. 3 divided by 3 is 1. So we have 1 over 1 there, times the same thing happens here. I can divide by 3 on top and bottom. That's going to give me 1 over 1 again. Now the rest of them, so this 3 over 1, I can divide the top by 3, but I can't divide 1 by 3. And actually, since it's 1, I can't really do anything with it. So I have to leave it as 3 over 1 times, same with back here, 3 over 1. Okay. So now we're getting a little more of a picture here. Let's simplify this. So when I simplify this, I'm going to have, well, 1 times 1, I can write that as 1 to the second power, times 3 times 3, I can write that as 3 to the second power. Down below, 1 times 1 times 1 times 1 is just 1 to the fourth, right? My next line down. Let's clean this up a little more. 1 to the second power, 1 to any power is just 1. 1 times 1 is still 1. So I can just put 1 right here. I am going to keep my 3 to the second power. And on the bottom, I have 1 to the fourth. Well, 1 times 1 is still 1, times 1 is still 1, times 1 is still 1. So I can actually just write 1 down here. 1 to any power or any exponent is still just 1. Now I'm going to go off to the side here. 1 times 3 to the second, 1 times 3 to the second, or 1 times anything, is just whatever the other thing was. So this is just 3 to the second. Now here on the bottom, this is still 1. But think about this. This fraction bar means division. 3 to the second divided by 1, anything divided by 1 is just itself. So my final answer is 3 to the second. Okay. So we expanded and evaluated there. Actually, evaluated would be 9. 3 times 3 is 9. But we do want to focus on this as the main idea of this lesson. Let's look at another example. So you might have noticed something that happened between right here and down here now. Let's look at another example, though, to make sure that the idea you might have holds true. So example 2, we're going to expand and evaluate again. Example 2 is a little different because now the exponent in the numerator is larger than the exponent in the denominator. So let's expand and evaluate this. We have 4 to the second over 4 to the fourth. That's equal to 4 times 4 on top, 4 times 4 times 4 times 4 on bottom. Now, we're not going to write as much for this one because we got through the foundational ideas up here. Up here, notice how we had 3 over itself, which reduced to 1 over 1, which reduced to 1 squared, which reduced to 1, which eventually was not there anymore. We just had whatever else was there. So when you see something over itself, like 4 over 4, with just multiplication in the numerator and denominator, those can actually reduce. They reduce to 1. So it is important to remember that, but those cancel out. So these 4s will also cancel out, but now we don't have anything left here. So we have to remember, oh, what can I put as my invisible number? We can put a times 1 and a times 1. These do not cancel out. 1 and 4 do not cancel each other out because they're not the same on top and bottom. So let's keep going with this. We do see 1 times itself, though, so we can put 1 squared, which is 1 to the second. And on the bottom, we see 4 squared. Okay. Now, if we go further, 1 squared is just 1. 4 squared is, well, I'm going to leave this as 4 squared, but 4 squared is 16. I do want us to focus on this, though. So the reason I want you to focus on this is because I want you to look at the exponent. Actually, let's back that up. Let's back that idea up. Let's actually go off of this a little more. So, if we go off of this a little more, the thing I want you to remember is that anything to the power of 0 is equal to 1. So we are going to do this. Instead of 1, I can put something that's the same value as 1. I'm going to put 4 to the 0 power, because this is still a value of 1. I'm just putting it in a different form. And I'm going to put 4 to the second underneath it. And we are going to go ahead and we're going to actually talk about something else for a second. I'm going to introduce to you the shortcut method for subtracting like bases with exponents. So the shortcut method is, and it only works if the bases are the same and division's the operation. We keep the base and subtract the exponents. So these are the two examples. Let me show you how short these can be. First we see how it's division and how the base in the numerator and denominator is just 3. So I keep the base, I subtract I do top exponent minus the bottom exponent. And it does make a difference. So look at this. We get 3. 4 minus 2 is 2. So we have 3 squared. That's the same thing we found by doing the expand and evaluate method. We found 3 squared to be the answer, which we know is 9. It matters which one you do first, because let's look over here. Again, we have 4 to the second and 4 to the fourth. We would keep the base and do the top exponent minus the bottom exponent. And what's kind of weird is we end up with 4 to the negative 2. So negative 2, what does negative 2 as an exponent mean? That is not the same thing as what we left off on with example 2. But look at this. If we use the rule for example 2, so just to remind you, we left off at this. We turned the 1 into 4 to the 0, because anything to the 0 power is equal to 1. And now check this out. We have the same base. That's the reason I picked 4 as the base. So I keep the base and subtract the exponents. 0 minus 2 is negative 2. So we have connections all over the place here. We have a connection between the shortcut and how to evaluate this. We have a connection between anything to the power of 1 and division with exponents. Math is a beautiful game. We came up with a shortcut method or a rule for dividing bases with exponents. Let's also look at another rule for if we get a negative exponent. Negative exponent, don't worry about writing that down again. But if we saw this, if we saw where we want to rewrite a fraction that has a base with an exponent on the bottom as a single base with an exponent, here's what we could do. Again, we could think of this. We could say, oh, this is like 4 to the 0. We still have 4 to the first. I would keep the base, do the top exponent minus the bottom exponent. We find out that 1 over 4 because remember, really, we don't need that power of 1 right there. We could have it. We don't need it, though. Is the same thing as just 4 to the negative 1. So the shortcut rule for negative exponents is that we can change the sign of an exponent by flipping the fraction. Have to remember, though, that bases stay the same and both exponents change to the opposite sign of the original. So if we go back up here, again, instead of doing all this where we did the division and the subtraction, let's just look at 4 to the first. 1 over 4 to the first. The rule is that I can flip the fraction, meaning 1 goes down here, base of 4 goes up here. The exponents change to the opposite sign of the original. I want you to also remember there's an invisible 1 as an exponent on everything if there is no exponent. So from here, we would change this to negative 1, and we change this to negative 1. And 1 to any power is just 1. 1 to the second power is 1. 1 to the millionth power is 1. 1 to the negative first power is still just 1. 4 to the negative 1 power stays as 4 to the negative 1. We don't need to put anything over 1. We can leave that invisible. And there we have it. So we have division shortcut for exponents, and now we have a negative exponent rule.